So there are many different integration techniques, and one of them is integration by substitution. Um, the goal of integration by substitution is to take something that might be considered complex and to put it in a simpler form, similar to some of our more basic integration problems where we were using the power rule. So notice here, we're looking to integrate f of g of x times g prime of x. And so the key to this is that we have some function g of x that possibly something else is being done to. It could be squared, or we could be taking the square root or whatever. And hopefully that kind of already makes you think about the chain rule. When we would have some, g of x inside of, let's say, some power. We had to deal with the power, and then we had to come and take the derivative of the inside. And that's what we're looking for here. Can I look at this expression as possibly some g of x inside of another function, and then here is the derivative of that g of x? If I can, then that's going to allow me to rewrite my problem in a simpler form, and we'll see that in the examples that we're going to take a look at. So let's start with this first example. We've got the integral of 8x squared plus 1 squared times 16x dx. Okay, so when I look at this, I want to ask, is possibly one of these things the derivative of the other? And the answer is yes. Okay, 16x is the derivative of 8x squared plus 1. So I'm going to rewrite this problem using U substitution. Okay, I'm going to let U equal 8x squared plus 1. Okay, I'm going to leave the power off because that's our outside piece, and we'll include it when we rewrite this thing. All right, and then it follows from here that du has to be 16x. So I can rewrite this integration problem as u squared, okay, because my u is 8x squared plus 1, and then we squared that, and then let's not forget this part, is 16x dx, okay? So we get du equals 16x dx. That's what I have right here. So now this is a much simpler form. We have the integral of u squared du. And of course we can just use our simple power rule for that. We're going to increase our exponent by 1 and divide by that exponent plus our constant c. Okay, and so now we go back to our original variable. That would be 8x squared plus 1 cubed over 3 plus c. Okay, so we were able to use substitution to help us with this. Now, this one was a pretty simple one, and everything matched up exactly. And so we didn't necessarily have to go through all of those steps. In a little while, we'll see where we don't have exact matches necessarily, and so we may have to do some manipulation. But for now, we'll continue to write these out. Sometimes you can still look at a problem like this and say, oh yeah, I can do it in my head because I have the exact derivative of 8x squared plus 1 here, and so I just need to add 1 to my exponent, that's what we did, and divide it by 3. Okay, but that only works if you have exact matches or superpowers. Okay, for B, we've got the integral of x squared minus 9 cubed times 2x dx. So when I look at this, if I'm going to use integration by substitution, I have to be able to identify one of these things as u and the other as du. And so it looks like it works out that u is going to be x squared minus 9, and it follows from here that du would be 2x dx. And so if I wanted to rewrite this in terms of u, we get the integral of u cubed du. Okay, because 2x dx is our du. Okay, let's highlight a little bit. Okay, here is u, and then this is du dx. Or rather, this is du. Du is equal to 2x dx. Okay, and so from here we use our power rule. It's going to be u to the 4th over 4 plus c, or x squared minus 9 to the 4th over 4 plus c. All right, it wouldn't be fun if we didn't put a little trigonometry in it. So let's take a look at c. All right, again, we have to, choose u such that its du is present. So when I look at this, I've got u is tan squared. Well, I'm going to choose u to be tangent x. Okay, the reason why I'm choosing that is because I know the derivative of tangent x is secant squared x dx. Okay, so just knowing and going back and looking at our trig derivatives. So that means I can rewrite this as the integral of u squared du. And in that case, we get u cubed over 3 plus c, or tangent cubed x over 3 plus c. Okay, let's do a check on this one. We can check these to see if we've done it correctly. So if this is my function, let's say f of x equals tangent cubed x over 3 plus c. Okay, when I take the derivative of this, I would bring the 3 out front, and those 3's are going to cancel. So that would leave me with tangent squared x, but then I got to come and take the derivative of tangent. We just did the derivative of the cube part so far. And so the derivative of tangent is secant squared x. And of course the derivative of c, or some constant, is just 0. So that brings us back to where we started. All right, here's another one. And if you look at this one, hopefully you're starting to notice a pattern. We could choose, you might think we could choose u to be cosine x, or we could choose it to be sine x, because they are almost the derivatives of one another. But notice that sine has a power on it. And so if we chose u to be cosine x, the derivative of that is not sine squared, it's just sine. So that wouldn't work, okay? But if we choose u to be sine x, then it follows that du equals cosine x. Okay, well, what about the square? Well, it's okay because we're just going to write u to the second power. So we're going to have the integral of u squared in our denominator, and up top we have du, because this is cosine x dx. Okay, so it's the integral of du over u squared. Or we could rewrite this as the integral of u to the negative 2 du. And we use our power rules. We're going to add 1. So that brings us u to the negative 1. We divide by that new exponent and plus c. Okay, or negative 1 over u plus c. Okay, or negative 1 over, our u is sine x plus c. All right, so for all of those we had exact matches. Okay, but what happens if we don't have an exact match? Okay, well, I think, we're kind of picking up again on the fact that we can have a, maybe, possibly the thing that's raised to the power should be our u, the larger function. That's not a clear definition, but I think you can see what I mean here. I mean, this thing is raised to this power, and then it's close, almost anyway, that 6 minus x cubed, the derivative of that, at least involves this x squared, right? In fact, it's x squared except for the multiple, right? We would have brought this 3 down front. So it makes sense that we'll let u equals 6 minus x cubed. And it follows that du is negative 3x squared dx. Okay? However, what we need to make a substitution for in our problem is x squared dx. Okay, not negative 3x squared dx. So I need an expression. I need to know what x squared dx is equal to. All right, and so I can solve for x squared dx. I see that du divided by negative 3 equals x squared dx. Okay, so when I come back over here, I'm still going to just substitute the way we did before. Okay, for 6 minus x cubed to the 5th, I'm going to say u to the 5th. And then for x squared dx, I'm going to say du over negative 3. So du over negative 3. Okay? Well, we have a constant multiple rule for integration that will allow me to bring this negative 1/3 outside of our integral. So we get u to the 5th du, and the negative 1/3 is on the outside. And now I can apply my power rule. Okay? And so we get negative 1/3 times u to the 6th over 6 plus c. Okay, or negative u to the 6th over 18 plus c. Okay, the constant is arbitrary, so we don't have to say 1/3 c or minus 1/3 c. It's just it ends up being some arbitrary constant. It doesn't matter what it is, because when we take the derivative of it later, it's still going to be 0. Okay, so our final answer then is minus u, so that's 6 minus x cubed to the 6th power over 18 plus c. All right, again, when we did our substitution, we needed a direct match for what was in our problem. And so in our problem, we had x squared dx. Once we decided what our u was, we were able to find du, but I needed to be able to substitute for everything that was here. We have a substitution for 6 minus x cubed to the 5th. Okay, that's this piece. And then for x squared dx, we found that it was equal to du over negative 3. So we substituted there du over negative 3. And then we were able to factor out our negative 1/3 and then use our power rule to continue. Okay, for b, we've got the integral of t cubed times the square root of 2t to the fourth plus 3 dt. Okay, so looking at this again, we can kind of say, well, the derivative of 2t to the fourth plus 3 is 8t cubed. So the only difference between the t cubed that's sitting here and the thing that is the derivative of this piece is the 8. That's just a constant multiple. So if the only difference is a number that we multiply by or divide by, then we can easily handle that. Okay? So I'm going to first rewrite this as t cubed times 2t to the fourth plus 3 to the 1/2 dt. Okay? And I'm going to let u equal 2t to the fourth plus 3. Then du is going to be 8t cubed dt. Okay, I can already see I've got nice substitution for this 2t to the fourth plus 3 piece, but now I need a substitute for t cubed dt. I don't have that yet. Right now I have an equivalent for 8t cubed dt. So to get an equivalent for just t cubed dt, I'm going to divide both sides by 8. So du over 8 equals t cubed dt. And so when I go back to substitute, okay, for 2t to the fourth plus 3 to the 1/2, we get u to the 1/2. And then for t cubed dt, I have du over 8. Okay, or we can write that. Next time we'll probably just go ahead and pull that 1/8 outside of our integral symbol, and then it'll just be du over here on the right. Okay, but that's what we'll do here in our next step. 1/8 times the integral of u to the 1/2 du. Okay, and so what do? We add 1 to our exponent, so that's going to be u to the 3/2, and we divide by that new exponent, okay, which would be the same thing as multiplying by the reciprocal. So we get 1/8 times 2/3 u to the 3/2 plus c. Okay, the 2 and the 8 are going to cancel, and so we're left with 1/12 u to the 3/2 plus c, or 1/12 2t to the fourth plus 3 plus 2t to the fourth plus 3 to the 3/2 plus c. All right, so here we have the integral of 6x squared over 4x cubed minus 9 cubed dx. And so looking at this, we kind of get a sense that if I take the derivative of 4x cubed, I would get 12x squared. Well, the difference between that and this is just a constant multiple. Okay, so we're going to let, in this case, u equal 4x cubed minus 9, and du is going to equal 12x squared dx. All right, I need a substitution for 6x squared dx. Okay, but I have 12x squared dx. So in this case, I'm going to divide both sides by 2. We get du over 2 equals, if I divide this by 2, it's going to be 6 x squared dx, which is exactly what I need. Okay, and so we get that this is equal to the integral of, since this is in my denominator, I can bring it to the numerator and make my exponent negative. So we get u to the negative 3. Okay, that's our bottom part. And for 6x squared dx, we're going to have du over 2, or 1/2 du. And so I put that 1/2 on the outside, and we've got du there on the inside. And so we can take the integral of this thing, and we get u to the negative 2, because we're adding 1. We're going to divide by negative 2 plus c. Okay, technically it's like that. Okay, and so we get 1, or negative 1 over 4 u squared plus c, or negative 1 over 4 times 4x cubed minus 9 squared plus c.